Today, in the first class of our workshop, we will discuss main introductory information for process engineering, which includes the standards and basically what we do as process engineers and what are one of the main things that we do are mass and energy balances, and we will discuss what they are and how we do it, basically. So let's go ahead and start with the standards of chemical engineering. I'm sure half of you, some of you already heard about these standards. And the main question is, why do we need to have any standard in the industry? The answer is actually simple because there is an experience and there is a knowledge that is accumulated in some part of the world that is more than the others. So they need to write that down and create these standards and produce recommended practices for all the other chemical facilities around the world. Which kind of practices does this standards include? It includes equipment sizing, their inspection, their maintenance, their performance evaluation, and these standards cover how it should be done. For example, as a process engineer, you want to size a pump. There is a certain way of doing this sizing procedure, and it is written by the standards. Two of the most famous standards are API standards. API stands for American Petroleum Institute, and ASME standards, if I'm not mistaken, American Society of Mechanical Engineers standards should be. And they provide methodologies. They provide procedures for regulating and guiding engineering design, inspection, maintenance, and etc. etc. One of the famous, some of the famous API standards that, as Talia mentioned, that we should know as process engineers can be API 510, which is for pressure vessel inspection. RP stands for recommended practice. API 521 is for pressure relieving and depressurizing systems. And if you want to know about what is overpressure, where overpressure can happen in which equipment, for example, in separators, how we need to regulate the overpressure scenarios, in general, all the things about pressure relieving and depressurizing systems is covered in these type of standards. Okay. For example, API 560 is for fire heater sizing, and it includes how we need to size and how we need to maintain a fire heater. Okay. Now we will see one example. For example, let's see what is API 560. I will try to open this. Let me see. Sorry. I will try to open this that I have here. And this link includes the introductory. You can also find this in the commercial website of API. And as you can see, it's API standard 560, and it is for fired heaters for general refiner service. Every standard starts with forewords and contents, of course. Now we will not be able to see the actual content, but I want to show you what is the table of contents in general. And as you can see here, it includes the design consideration, how we need to size tubes, what we need to consider. It supports everything that you can ever imagine about fire heaters. It is included in this standard practice, okay? And obviously, these are super big documents, and it is better for, if you are a professional process engineer, it's better for you to know every standard practice. And same also can be said for ASME standards. They are usually for pumps or compressors or other rotating equipments. Yes. Then, if you have any questions about anything that I covered during this session, please type to the chat or raise your hand. I think I can see when you raise your hand, and you may open your mic and interrupt me to ask your questions, okay? Then the next topic that I want to mention is, what do we need to know in a topic basis in order to be a successful and competent process engineer? there is specific, very, very important topics that we need to know. And it is better for you, of course, to learn them by heart. First is very, very essential one is separation processes. What do we need by separation processes? One of the most famous topics in separation processes are, for example, distillation. Next question can be, okay, what we need to know about distillation. You need to know what are theoretical basis of distillation, how vapor liquid equilibrium works, which kind of equations can be used, what are the types of materials that we separate with distillation, how distillation is operated in industry. Okay, then it comes, of course, the more engineering part, which is included the operation of actual columns, how we operate columns, how we size them, which kind of excess equipment do we need to size them. Then, if you know distillation, it's super good, and there is a lot of people. Their only specialization is only distillation. I would say it's such a big and huge topic. But for now, it is better to know essential information from distillation and to go to other separation processes, which can be absorption, adsorption, which can be other liquid extraction, for example, and etc. etc. There is so much separation processes going on in the chemical industry, and you can. It is better for you to know how they are applied in the industry and what is the theoretical basis on that. Why you need to, actually it is also can be said for all the topics that has mentioned here. When you know the theoretical basis on the engineering topics that we talk about, it gives you confidence and it gives you more reliance on your knowledge, and you will be better when you make deductions about what you are asked. Okay, you will in interviews, technical interviews, you can be asked how you would handle this engineering problem, and only if you know the theoretical basis you can deduce some good conclusions about the question that you asked. Okay, so one of the essentials are separation processes. Next, and obviously the introductory topic would be mass and energy balances. What is it about? As it can be seen from its name, mass balance is, for example, let's take some unit. Let's take some pump, for example. Let's draw a rectangle which resembles the pump, which imaginary pump. And obviously we have some inlet stream and we have some outlet stream. Mass balance, by doing mass balance, we would know which kind of material and material and how much of this material comes in and comes out of specific unit. Okay, simple version is pump. We know that whatever comes to pump is equally comes out of the pump. It is the same, nothing changes, because we don't separate or we don't produce or we don't do anything if we use pump. But when our our analyzed unit changes, say it can be a separator, simple separator, or it can be a reactor. Of course, with this type of units, we need to calculate, we need to do mass balances, so-called mass balances, to calculate what comes to the reactor and what will come out of the reactor after the reaction happens. Same can be similar process can also be said for energy balances. But what is the difference? In energy balance, we calculate how much energy comes to the reactor and how much energy comes out of the reactor. Why we do this? Because by doing this, we can know how much, for example, cooling do we need to use, how much heating medium do we need to use, and they are super important in the operation of these reactors, for example. They are very basic, and the calculations and the equations that we use in mass and energy balances are not complex at all. It is easy, but it is absolutely essential for every engineer to know about them. Okay. Then, of course, it comes the design. Design is the next step. As soon as you know mass and energy balance, design comes as the next step. This design includes what mechanical. It is somehow correlated with the work of mechanical and sometimes maybe electrical engineers. We have a lot of intersections between their work and our work. So these designs include, okay, you know everything about theoretical basis of distillation, let's say, but physically, how and what size of column do we need to build? This can also be some other equipment, pump. Okay, you want to increase a pressure of A to B, but what will be the actual size of a pump when you want to do this operation? And that comes out of design. Okay, then it comes economics. Economics is about money, and it is super important too because, as you know, oil and gas industry and chemical industry are one of the most biggest economic industries in the world, and they are also one of the most profitable ones. Therefore, in every engineering project, economics leads first, I would say. And which kind of calculations do we need to use? You need to estimate basically two things. First is called capex, which means capital expenditure, and the second is opex. Okay, capital expenditure and operational expenditure. Capital expenditure, capex, is what is the cost of building a column, or what is the cost of building a chemical plant. This includes uh, CapEx is said to be paid only one time. Once you build an actual plant, you will never need to pay again for that. Okay, but OpEx, you need to pay, let's say, on monthly or annual basis. This, for example, this can include the construction costs. This can include the equipment costs. You need to buy the equipment. Usually in the industry, the way of working is that you design as a company, you design equipment, then you order. There is some specialized companies who, for example, only produces a distillation column. And you order them with the specs that you have. You send them your specs, and you order a distillation column that is specifically designed for your needs. Okay, this includes capex, and opex is what you spend during your operations. Usually, chemical plants are designed to operate between, I would say, 20 to maybe 40 years, 50 years. This is the order of magnitude is tens of years. Okay, they are not designed to operate 100 years or 200 years. It's too much already 40, 50, 50. And during those years, you need to, for example, if you want to operate a distillation column, you need to buy a heating and cooling medium. And it's not free. You need to spend some money to basically create them, to create the heating and cooling medium. And that is included in OPEX. And some of the process engineers' work is to calculate this economics. Next topic I want to mention is fluid transportation. Fluid transport, as you know, in most of the chemical industry, let's say, we are dealing with continuous processes. Okay, we will talk about it later in steady and unsteady process. Just to let you know, in chemical industry, we are dealing with continuous process. What does it mean? We have piping, and to join different units, we are using piping equipment. Okay, and in this piping equipment, we are mostly dealing with either gas or liquids, so-called together fluids. And for this, how the fluid transportation or so-called fluid mechanics and dynamics deals with this problem. How gas or liquid goes from one unit to another unit. There is a lot of calculations and a lot of um, equations that you may use in this topic. If you go a bit deeper, there is even newer concepts that's called computational fluid dynamics, and they're simulating how fluids would behave in certain environments. And it's absolutely essential too to estimate theoretically estimate the behavior of liquid in our system. Then it comes thermodynamics, and one advanced version of thermodynamics is multi-phase thermodynamics. Why do we need thermodynamics and what is it about? It's again one of the theoretical topics. And by knowing thermodynamics, you will basically understand how heating and cooling how heating and cooling works in our nature. Thermodynamics is basically about the nature of materials, I would say. And by knowing thermodynamics, you would know how heat is transported from one material to another material. Besides, you would know how and also why and in which conditions. Multiphase thermodynamics, as it's known from its name, multiphase comes from when you have more than one phase. And what is phase in engineering? We call phase as a material which is homogeneous in its whole volume. For example, imagine a liquid, okay? If it's only water, let's say a glass of water, it's of course one phase. But when you introduce a gas, for example, a CO2 gas, it will become a two phase because we have two separate homogeneous volumes in our system. Okay, and multi-phase thermodynamics deal with the heat, the transportation of heat, I would say, between liquid and um, gas, or it can be another. Also, can be different phases, can be supercritical phases too. Okay, then it comes reaction kinetics. This reaction kinetics is mainly about what are we doing inside reactors. As you know, as it is explicit from its name, chemical industry is based on some reactions. When you put two materials together, they would react and they give another materials. And basically, kinetics, the word kinetics comes if ever in your life, if you see any word about kinetics, you need to first think about a time. Okay, kinetics shows how fast a reaction would evolve and from which conditions does it depend on. For example, if you have some kind of system which is, so let's say, exothermic, if how the system's um, so-called residence time would behave if you increase the temperature or if you decrease the temperature, if you use a catalyst or if you don't use this catalyst but use another catalyst, or maybe if you don't want to use anything. These topics, the main question is how fast the reaction occurs. These topics is within the scope of reaction kinetics. And then it, it would be joined to a bigger topic, which is called reactors. In reactors, we not only deal with reaction kinetics, which is about time, we also deal with mass and energy balance, of course, and thermodynamics. With knowing thermodynamics, you will know what can be added as a heat, or maybe it should be withdrawn. The heat should be withdrawn from a reactor. And then lastly, it comes control. Control is super important in our chemical industry. Why? Because small sneak peek from the next slides would be because we want everything to be in steady operation. Okay, unsteady operation comes with a lot of disadvantages. To make everything steady, we need to control it. Okay, and our work coincides with, again, process automation engineers here, and the basic calculations in control systems are the design of control system, the creation of control loop, so called, and also what are the transfer functions and what are the some mathematical equations can be used to control. Okay, any questions about standards and the topics that I mentioned here? Do you have any questions? Okay, I cannot see any hands, so it means you don't have any questions. Good. Then we will go to drawings. Main chemical engineering drawings are including BFD, PFD, and PNID. BFD is the simplest one. And also bonus, we have cause and effect, which I will talk about later. Okay, firstly, we need to start from block flow diagram, so-called BFD. What is that? As you already saw in the quiz, it is an initial and simple visual form of production facilities, but provides only limited information. Let's see, this is a simplest, I would say, very typical BFD of refinery. Okay, and as you can see, all the units are just described with one rectangle and a text written on it. For example, hydrotreater. You don't know what is in hydrotreater. You only know what it comes, and super generically, what it comes and what it leaves. You know an isomerization plant, but you don't know what is isomerization plant. You don't know which kind of equipment do you have, which kind of control do you have. It is super simplest one. Okay, this is what we do in feed stage, engineering design stage, and this is one of the first products of a chemical engineering project, I would say. Then we go even more deeper. We go to process flow diagram. Process flow diagram includes material and energy balances. And in usually in process flow diagram, we expand, for example, this unit. We treat each unit separately and we expand one unit. For example, in each flow, for example, let's see, this is one flow, okay? This is an absorber, and what is the upstream of absorber? As you can see, we have different streams, and each equipment, the significant point in process flow diagrams is that each equipment is shown one by one. And in between streams, we also need to include mass balances and energy balances, okay? We need to know what is inside of each stream. But again, here we don't see one by one sketch if we compare it with what we see in real life in industry. Okay, this is again a bit general, but more specific compared to BFD, but more general compared to process and piping and instrumentation diagram, so-called PNID. Okay. Last words about PFD is that we need to typically include flow rates, chemical compositions, phases, temperature, pressure, viscosity, thermal conductivity, specific heat, anything about the material inside our piping and our equipment. Then the most detailed one, the most detailed diagram is piping and instrumentation diagram. In this diagram, we need to show everything that you see with your eyes in when you visit a chemical plant. This includes every detail of equipment, every detail of piping, valves, if we have vents and drains, if we have any instruments, any emergency systems, any control loops. This is also one of the most significant parts of piping and instrumentation diagram. You be able to see control loops. We don't have that in PFDs. Usually, we don't have that. Usually, and the materials of construction and any strainers or any traps should be mentioned in piping and instrumentation diagram. This can be one of the examples, one of the simple examples of piping and instrumentation diagram. Here, what you see is a bit more specific, I would say. Why? Because the most significant thing is you see control loops. You see that in every equipment, which parameters are controlled and how they are controlled. Okay, that is one of the valuable informations. You also need to be able to see all the valves and all the details of your equipment and also your piping. How big is your piping? From what material you construct your distillation column, or from what material you construct your piping? All the information is included in piping and instrumentation diagram. Then The last thing is cause and effect diagrams. Cause and effect diagrams are, as it is known from its name, it's also called the fishbone diagram. We have some effects, we see some consequence, let's say, and we are brainstorming to find what can be a causes of this effect. Okay, we are finding several causes. It's something like this, also called the fishbone diagram. Several causes may be ended with this specific effect, and this is how we construct this diagram. Okay, then we go to steady and unsteady process. Point of view, if you want to manage some problem in general, be it an engineering problem or be it a general problem, you always want your conditions to be steady conditions. What does it mean? It means that during your process, your main let's say condition, what I mean when I say condition is your temperature, pressure, flow, composition, and sometimes level too. These are the pretty much all the conditions that we want to be steady. Okay. In we, as you know, as some of you know, we may have two kinds of operations in our industry. One is called continuous, and one is called batch. Okay. In batch process, imagine the batch process as maybe cooking a food. Okay, you add everything to pot, you open the gas, then you just wait and don't do anything until it cooks and you start eating. This is a batch process. As you know, process conditions constantly changes. Your composition changes, your temperature, your pressure, everything changes with time. But in continuous process, and continuous process can be an example of what we seen in the previous diagrams, let's say 90 most of the times, if it's not a specific process, most of the times we are dealing with continuous process. Okay, and in this continuous process we want everything to be steady without changing. And that's why, in order to have a steady process and not unsteady process, we have a topic that's called control. Okay. Yes. Next, I want to talk a bit about material balance. As I mentioned earlier, material balance are fundamental. It's the one of the first topics that you learned probably already as a student, and it is actually one of the daily jobs, day-to-day jobs of a process engineer to calculate mass balances. Of course, as a student, you are dealing with more simple systems, like this can be a simple system. For example, we are having a filter here, and from filter, we have bunch of inlet streams, a wash water and solvent stream, and a suspension stream. We have different chemicals inside here. Usually we are dealing with mixtures, not with pure chemicals, let's say. And here we have inlets and solid, filtrate, and our wastewater and are our outlets. So the main thing, the main aim of calculating mass balances are what comes in wash water and solvent, and how much of, for example, in wash water we have some amount of water and some amount of some chemical, says X chemical, and how much of this water is in filtrate, because it divides how much of this water is in filtrate and how much of this water is in wastewater, let's say. That is our aim, and that's our calculation, just to know the composition and the amount of everything. And by doing that, we also need to know a very, very important concept, which is called recycle. Recycle, it is very common to use. Why? Because In laboratory experiments, when we do reactions in laboratory experiments, for example, we want everything to be pure. We start with pure components. We have perfect conditions for reactions. Then we, of course, get 99%, 999 yield, and our selectivity is super high. But that is not the case in industry. You may ask why. Um, First is conditions, I would say. Conditions are cannot physically be as pure and as specific as we have in laboratories. And the second may be economic, because creating those conditions may cause a lot of uh, resources, a lot of not only monetary resources, but also all kinds of resources. And that's why we always have some unreacted or out of spec products. Okay. For example, we have some reaction, CH4 plus oxygen goes CO2 plus H2, for example. And of course, not all of the methane or not all of the oxygen is going to react. Some will exit with the exit stream, no? And that's why we have what's called separators, and that's why we have separation processes to separate unreacted ones with the reaction products and then send them back to our initial stream to just increase the yield and increase the so-called efficiency and effectiveness of our process. Okay, good. And if you talk about energy balance, you may imagine what we have generally. We have energy balance in every type of equipment, in every equipment. But usually, if you think about one of the simplest heat exchangers between fluids, the operational basis of heat exchangers are, as it's known from its name, to move a heat that is trapped in one fluid to another fluid. And how we can do that? We need to use some thermodynamic background and we need to use some thermodynamic equations to do that. And why? What is the point? We cannot just make them meet and exchange heat. No, because think of energy as money. Because everything doesn't matter if you want to decrease an energy or increase an energy, you will spend some money. Okay. And main aims of operation, let's say, and main aims of why we have a job, so-called production engineers, are to save money and to be as efficient and as profitable as possible. Okay. Therefore, in order to know how much energy do we need and how much energy do we exchange between fluids, we need to do energy balances. And usually, how we do it, mathematically speaking and thermodynamically speaking, we have a thermodynamic property that's called enthalpy. Enthalpy. I'm sure some of you knows what is that. I will not go into very deep details, but if you want to evaluate a system's heat under constant pressure, that is called an enthalpy. Okay, and how we do the energy balances? We evaluate firstly, of course, we start with the measure of energy. You should know what is the measure of energy. It's the temperature, no? And we start from some conditions, temperature, pressure, and the composition, of course. And by inletting all those conditions, we are calculating what is the total enthalpy of our inlet. We do the same for outlet because usually it is done after mass balance. So you know what is your temperature, you know what's your pressure and composition. Energy balance is usually done after we do the mass balance. So you know the total enthalpy of your inlet stream, or if you prefer, total energy of your inlet stream and outlet stream. Then you just subtract it, and you know how much energy should be provided to your unit, or how much energy should be withdrawn from your unit. Okay, and that's basically how we do the energy balance. It is easier to talk and easier to speak. But the calculations may be challenging, because heat balance calculations also include some knowledge about the heat transfer process. And in heat transfer, you need to know materials properties. And to do these calculations may include higher level of mathematics from you. And sometimes it may be challenging, sometimes it may be a bit easier. Okay, now, if you don't have any questions, if you have questions, it's a good time to ask. That was all I wanted to present today. Um, I cannot see any hands, so I think you don't have any questions. So what we will do now will be a case study. Okay. Here, what you see is piping and instrumentation diagram, PNID. It's a PNID of a distillation system. As you can see, this is a T101 distillation column, and you have all kinds, if you know all kinds of equipment that is related with your distillation column. V104 is so-called reflux drum or overhead receiver. This E104 is a condenser, and E106 is a reboiler. Okay, and we have some pumps to recycle our product back to distillation column, and also to as a distillate, as a product. Okay, so what I want to discuss with you will be these two small tasks. First, by reading this PNID, now we will assess your PNID reading skills. By reading this PNID, can you tell me how the level of overhead receival is controlled? That is your first task. You can type in the chat and I may read, and then we can discuss. I will give you some time for that. And then the second question is, how is the pressure of distillation column is controlled? And first is describe, please, how you know what is the pressure control of this column, and if you know any other way of controlling the pressure in the distillation column. I think for this task, you might have 5 minutes. Now it is 49:50. I think you might have 5 minutes. Type your answers to chat, and after 5 minutes, we'll start discussing. Okay.
So last 1 minute, guys, for your dropping your answers here. Chingiz, we still have two answers from Elton and Issa. Elton mentioned about the first question, like level controller, and the second, increase or decrease flow and add PSV. And Issa mentioned that, so level control to measure the liquid level in the vessel. Let's wait for another 1 minute and then we can discuss, I think. Okay, time is up. So Chingiz, if you want to, I can read the other answers. So Aisha mentioned the first question like level controller, and the second one pressure controller on top stream of V104. So let's discuss if you want, and then you can ask your questions.
Yes, thank you very much, Talia. Okay, let's start with the first question. The first question is how the level of overhead receiver are controlled. Let's see what we're talking about. We are talking about V104, this guy. We're talking about this. And we want to see how the level is controlled. Level is usually in PNIDs, piping and instrumentation diagram. You start to see a control loop that starts with L, which starts for level. Okay. And here, what we see around V104 is LELT, LIC, LY, LCY. When you say that, okay, it is controlled with level controller and again, level controller, yes, that's correct. If you talk technically, that's correct. But any controller that controls the level, it's called a level controller. But what I expected from you to answer is by which stream, maybe I need to be more specific, but by which stream are we controlling it? And the correct answer would be the flow of distillate. In our case, the distillate is benzene. And you see, we have LCV. LCV stands for liquid control, well, level controller, sorry, not liquid, level control valve, okay, LCV. Normally, control loops are consist of three main elements. One measures, LT measures, transmitter. Then we have the controller equipment, which in this case is LIC, level indicator controller. Then we have an action element, which is called LCV, level control valve. Okay. So in this loop, if we evaluate this loop, basically, we would see that we have this valve here. And with using this valve, if we increase the flow of benzene, so-called, if you open the valve, then the level will decrease because you see we have a control connection with this valve. And if we decrease it, or if we do vice versa, if we close the valve, then we have increase in the level. Some, I guess, mentioned for example, sorry, I can see the answers in this chat. Samra mentioned level controller when the liquid reaches to HHL or LLL, the valve is opened and closed respectively. And also, I guess, okay, this is next question. Then level controller for, okay, good. One thing that we need to differentiate should be the existence of these things. So-called Samra also mentioned HHL, LLL. What are they? They are called safety. They are safety measurements. HHL is high level and LLL is low level. Here you see we have LAH, that is that stands for level alarm high, and we have LAL, and sorry, LAH, level alarm low, level alarm high. This is okay. This is joint and connected for control, but it is mainly a safety measurement. Okay, in daily basis, day-to-day basis, it will be better to say we control it with flow of benzene rather than saying that okay we have a safety equipment. Okay, that is another topic I would say. Okay, close to the scope of control, but I would say different branch. Okay, so good. Any questions about this topic? About the first question. The controller using level control to measure the yes, using level control to measure. Okay, one question. One I would say notice that I need to do is controller doesn't measure anything. Controller only controls. Well, and what I mean by control is comparing the set point with real data. It just compares and sends a signal to action element. What measures is this LE guy here, and transmitter sends the signal to our controller. Okay, measurement is done not in the controller, within the control loop, but not in the controller. It's another equipment. Okay, level controller, we have level controller when the liquid reaches to HHL that we discussed. Okay, okay. I guess we're done with the first question. Then let's go to the second one. The second one is how is the pressure of the distillation column controlled? Let's firstly read your what you wrote. Okay, hold on. Increase decrease flow. I agree, flow, but you need to be more specific. Flow of what? Flow of something. And you need to specify which flow is that. And add PSV. This is again what I told. This is PSV is pressure safety valve. This is a safety equipment. It is joint to control loops, but it is not in the main control scheme. Okay, you need to remember that. Then, with the pressure of controller of the upstream, okay, pressure controller again, good answer. I technically agree. Yes, pressure control condenser duty can be used. Amazing. Yes, that we will discuss. Well done, Samra. That is one of the things that I want to mention. Then we have pressure of the distillation column controlled by the regulation of flow rate of cooling medium. Amazing. That's also one of the things that I will mention. Good. Uh, then PI on V4, vent flare, full gas, PI, decrease, increase, condenser, CV, flow rate, increase, reflux column. Good. Good. Yes, amazing. So most of you found alternative answer. Here, how we control it with the flow of fuel gas. Alton, the correct answer is flow of fuel gas. Here you see in the usually liquid streams, we draw it on the under the equipment. If you have something flowing as a liquid, it's under. When we have something that is flowing as a gas, it's upper of the equipment. So we have a line that is that clearly shows that fuel gas is transported with this line, and we have a main control valve, PCV, pressure control valve here. And as you can see with the flow, by opening of this valve, we can control the pressure of a column. That's perfectly makes sense. Yes. Uh, and the next answer, what would be? What are the other ways of controlling the pressure? Our colleagues mentioned correctly that condenser duty. Here is the condenser, and if you read, see this first is cooling water, and the second is cooling water return. Okay, if we have a control valve here, and if we join this control loop, this pressure control loop to this control valve or any other control valve, we can also control the pressure by controlling the flow rate of cooling medium or so-called condenser duty. That's I perfectly agree. Ainur, amazing. Yes, that's good. Yes, that was the answers that I expected. So that's it from my side. Thank you for listening. If you have any questions, you are welcome to drop them in the chat and I will read them. Thank you. Yes, Nazan.
Thank you very
Yes.
much, Cengiz. Okay, yes, Nazrin has a question, I think. Yes, Nazrin, please.
Yes, first of all, thank you for the session. I had only one question about the vent to flare part. Here, the stream does not have any valve or something, anything. I mean, how we control how the venting to flare here. The
7.
seven,
This
yes.
vent to
Uh-huh.
flare. Let's see. It comes from the overhead drum, no? Let's say if you have an emergency situation, if you in the downstream of the equipment, for example, fuel gas goes to, you see this line shows the battery limit. It goes outside the battery limit.
Mm-hmm.
Okay, something happened in the downstream process and we need to cut the fuel gas. We need to have an emergency kind of an emergency exit in planes. We need to have some line for that. Okay, if the downstream of this fuel gas is trapped, is blocked, and we cannot send, and we need to cut this line, but while if we want to keep producing, because as you can see our main product is benzene and toluene here, it's just the separation of benzene and toluene, so we can send our fuel gas with this line to flare. This process is called venting. Vent to flare comes from that, and flare is another system.
Yeah, I got this part, but generally we don't show as line or as valve or some control in the in this PNID, or generally it's shown, but it's simplified version here.
This is also this is also simplified version, I would say. Every company has its own rules and traditions of sketching PNIDs, I would say. It
Mm,
depends.
okay.
It depends on who
Okay.
sketches the PNID. Can be shown, cannot be shown,